Good morning. Welcome, everybody. I am going to be doing more Random.Code this morning. I forgot to get my little music player thingy going here. So let's say play all. Turn that down a little bit because I was playing Splinter Cell last night, so I needed to increase the volume a little bit. Anyway, I did solve part 1 of day 16 finally. I did it off camera. I was actually working on part 2 of day 17. Part 1 of day 17 actually wasn't too hard. That one was pretty easy to get in place. Part 2 is harder, but I did spend some time looking at it and trying to narrow things down. I still don't have an answer for it, and I don't want hints, but I'm going to shelve that for now. Because last night I started going, why didn't my solution work, at least hopefully as well as I wanted it to? It still takes a little bit of time. It still takes like 20 or 30 seconds or something like that to run. I'm going to run it again just to show you because I got to do something real quick on it for part 2. But the thing I realize is when we do the pruning, and in fact I can get rid of all this commented code now, is when I do this pruning, I had it a little bit more complicated. The deleted code showed that, and I didn't need to do that. I just need to say, go through each path and then determine if there are any paths that are not that path. But the visited junctions thing, I needed to not be equal. I needed to do something a little bit more specific. I need to say, is the position the same? Is the direction the same? And is that cost less than or equal to what I have? And if there are any, I can remove myself. And then I just keep going through the for list until that gets to the end. And then those are my paths to evaluate. This still may not be perfect, but this came back in time and I came up with the answer. Now, the one thing I want to do here is when I create a new path, visited junctions here, I do want to put in a new visited junction where I have a new position of how do I not know where to start? I go with the map, reversed count, number of turns. Oh, the key. Duh. I was like, I gotta know where I'm starting. So actually I can just say that. Direction east. Traverse position count is 0. And the number of turns is 0. Okay. The reason why I'm putting this starting point in here is because of part 2. And I want to just make sure that this does not screw anything up. The number of turns to go north was 1. Okay, so let's run our tests. They all pass. Okay, so let's go to our program. We are running day 16. We have part 1. So now you're going to see how slow it takes. Okay. And I'm just going to do that because we don't want that in play right now. So you can see it goes up. The increasing around 400 starts to go down again. So that's where I was like, let's stay on the struggle bus. And as you're going to start to see, it will go down and then it comes back up a little bit more, but then it goes down again. And then it will just start to descend to nothing. So I'm sure there's probably other optimizations I can make in this, but I was like, it's good enough. So you can see it. I don't know how long that took, but it feels like about a 30-second run. And that should be the same answer, 92432. 92432. Yes. Okay. So The second part of the problem now says that basically you can read it. I usually read these, but I'm not. Basically, what you need to do is when you find the best path, you actually have to find the best paths, plural, one or many. And so as you can see here, this map, let me zoom in on that a little bit. This map actually has multiple best paths. Like here you can go up, over. This one is up and over, and it's the same cost. Same thing over here. So what you want to do is, it talks about benches and best positions. What you need to do is find all of the positions, unique positions for all the best paths, and get that count. So this is 45 tiles. So you'd go this way, up and over. This one you'd also go up and over. This one wouldn't be counted more than once. It would be counted, but not more than once. So hash set time. And the reason why I put that first thing in here and made sure that that didn't screw things up is because what I realized is, as I'm going through and finding all the best paths, I'm going to have to change this a little bit for part 2, but I thought, well, I know all of the visited junctions. And in fact, I believe, like when I go east and I get a visited junction to the end, I'm also adding that, because you have to include start and end as well. And so what I said is, well, if I find a best path, I know all of the routes I've gone, I know how many positions it takes to get from what to what, and so I can create all those positions and put them in a hash map. If I find one that's, as I'm doing my search, that has a better cost, then I just wipe out the map and then calculate that one. So I think that should work. So I'm going to get into that right now. By the way, if you're new to the channel and you haven't subscribed, please subscribe. I would greatly appreciate it. It's funny listening to streamers talk about, I'm trying to get to 1 million. I'm just trying to get to that 1,000 goal. So if you wouldn't mind doing that, I would appreciate that. All right. So I basically have to do the same thing that I was doing up in part 1, except completely different. So let's do run part 1, and we'll do run part 2 here. Okay. We still need to keep all this, more or less, but there's also something else we're going to need to do. We need to have var best locations as a new hash map, hash set, sorry, of positions. And then what we return is the number of best positions. There. Okay, now of course we got to actually do this. So we get an X path, we say is it finished, and we minimize by current cost. Okay. Now, of course, this is a little different because we can't just find the minimum. We actually have to find all of them that are the minimum. Okay. So I think there's a group by, and a link with group by always throws me. I'm probably gonna have to look it up, but we want to get all of the ones that are finished, and we want to group by, and again, I don't know why. I don't know, there's some things that work really well and some things that also don't. Group by always throws me. I don't know why. And of course, if you look at the help here for this, it's like, yeah, how is this helpful? This seems to help, right? And I'm going to harp on this for a little bit. When I was doing my master's thesis way back in the Stone Ages, there's lots that I learned about it. One of them was when my advisors were reviewing my thesis before I actually had to do the presentation / defense of it. When you do a master's thesis, at least when I did it, you're not doing something like a doctorate is typically something new, and your dissertation defense can be very, very difficult. A master's thesis is showing what you did, being able to defend it, but you don't have to, at least I didn't, you don't have to like defend anything you could have possibly been taught or whatever. So the one thing that I got from my advisors, especially my head advisor, the guy that I was doing the work for, it was basically show examples. Like he said, you're actually you're into the weeds with all this stuff. You're basically giving me and these other people summaries. We don't spend all of our time on this. You are. So what may make sense to you doesn't necessarily make sense to us. Show us examples that will help. And that has stuck with me now for almost 30 years. It's one thing to explain it and you want to explain it well, but you've got to have examples. You got to show how this actually really works. And so something like this is much more helpful than what the hell is this? It's great. You're doing this work. That's fine. But something like this is really what I'm looking for. Okay. And so I want to group by, let's see if I can see if this actually is, I want to group by, the cost. So I group by the cost. And then I think see, it kind of helped, but it kind of didn't. So what I want to project out now, given that, is and so what does this give now? The key is the cost, and then you get the path back, which is fine. Min by the key. And so what does this give us here? This gives us a grouping of, because we're in 2, right? Yep. Okay, good. So if that key and then I'm assuming we get the value. How do you get the value out of this? Well, fine. We get the key there. If that is less than that, then we say fine. Now we need to Um, let's do this. Next pass where it's finished and that current cost is less than or equal to our minimal cost that we currently know. Yep. So we're going to get those, and then we say group them by the current cost, and then we want to get the minimal group. If it's strictly less than that, now we say best locations clear. Okay, because either we found ones that are less than, or we found ones that are equal to. If we found some that are less than, then we just clear. And now what we're going to do is we're still going to add new paths there. But now we're going to say for each var best path in minimal that's a path. Okay. It's weird because it feels like this should be like a definitive. And if it isn't, well, then we're checking it here to make sure that we don't do something with a null. Whatever. So now with each best path, what we want to do is find all the locations of this path. Okay. So we're going to say for each var visited junction in best path visited junctions, except not quite. What we want to do is for var j is equal to 0, j is less than best path visited junctions count -1, because we want to be able to look one ahead, as you're going to see in a moment. J plus plus. At least that's the thought. Okay. What's the problem here? Oh, it's length -1. I always get confused. Which one is it, length or 1? So we go through all the junctions. We're going to find var head start junction is equal to that, and then var end junction is j plus 1. Okay, because we're going to hop to one to the other, and then the next one we're going to go from that one to that one, and then the next one from that one to that one, and so on. Yeah. And so now we need to do some directional logic. And again, I could probably make this better, but whatever. Okay. My wife had to stop. She had to go to the urgent care because she thought she had a sinus infection, and they said, yep, you do. So it's interesting, another rant. I remember years and years ago, if you were sick, and I get it's a Sunday, so most GPs and stuff aren't open, but if you're sick, it's like, okay, I could get in today. These days, you can't use a GP to do anything that's kind of like, I have a sinus infection, I have a fairly bad cold, like GPs are something that you can schedule for something that's in the future-ish, like a yearly update or something. It's just, I don't know. It's a little weird to be like, I got to go urgent care. It's like, well, is it urgent? I guess, whatever. So, but usually people are like, oh my God, you're going to urgent care. No, well, yeah, but it's not like it's urgent. It just, I need to have it, whatever. Okay, so now we need to say if start junction direction is equal to, we'll say direction east. We'll start with that. Okay. And we'll get the other ones in. And remember to do else. South. Else if west. Else. Okay. So now we're going to basically say, whoops. We're going to include both the start and the end, and that will do doubles because we're always going to be doing this, the end as the start of the next one. But that's why we're using a hash set. And I'm sure I could do this to be a little bit cleaner, but it's fine. We only do this evaluation once we get a valid path. Okay. So we're going to say for var d is equal to our start junction position. We're going to go x. Okay. D is less than, we'll just get that in there and evaluate that. Yes. So now we say best locations dot add new position where the D is that, and we don't care about what the Y is. Okay. And then we do the same for south. Our direction here is going to be, our start is Y, and this is increasing. So yeah, that's increasing that way. Start junction south is increasing that way. And so this is now reversed. X, D. Now here's where it gets kind of a little trippy. If we're going to go west, it's the same thing as going east, except you're starting at the end. And your end is your start. Okay? So it's basically saying, oh, you're going from here to here, and you could do the negative, but you can just do it from wherever that is to here and do the east, right? And just reverse it. And then it doesn't matter. And then the same thing for going south. You're going to go north now. And so it's the end junctions and then the start junctions Y. Because the end is the start, and wait, let me think about this. Yes, because the end would be like a 3, and the start would be like a 6. And so you just want to plow through those points again. So that should do it. And so again, if we do this, if we found a new one, we clear it out because now we need to do this. Otherwise, either way, we either have something that's equal to or less. If it's equal to, we're just going to be adding all of the ones we just found. If it's new, we're putting into a new hash set. And so now what we say is we get new paths, add range. We'll still keep doing that logic, except now what we want to return is and this best locations is only for ones that have finished that were under. And then we're going to look at the ones that haven't finished and only ones that are under the current cost. They could be substantially under, but if they're at or over, they're already thrown out because there's no way that they could get any better. And then we do some pruning to see which ones we can remove from that. But I think that should work. And so I think in this one, well, I think it should work. And then I found out with this one how much it's kicked my butt. So in the small and large. So we do have two test cases, 45 and 60. So we have part 1 large and large. Those other two were submitted by somebody, but I don't know what the answers are to that. I just want to see what I get for the 2. So if we say part 1, part 2 small, and we run this with 2, what we should get is 45. Okay. And then the 2 large, and we run 2 on that. Whoops. We should get 64. Let's see how wrong we are. Yeah, 2 failed. Ah, of course. Of course. It's probably my what was it? Giving as a object is a null. Yeah, no reference exception. Okay. Yeah, okay, I'm being stupid because we may, as we're starting, not have any that finish. And so this has a defensive check around it. In both cases, we want to say if this is not null. So, okay, and then we're going to move this and this within it. Okay, that was just stupid coding. And then we don't need to do this. And then we don't need to do this. One passed. Which one passed? The large one passed. That's interesting. What do we actually think it is? 37. So in the large example, I'm sorry, in the large example it works. In the small one, it doesn't. I'm just curious. What do we get if we run this for the part 2? And are we too high or too low? I'm just... Do we get lucky? I highly doubt we're going to get lucky. I bet we're going to get an answer that if it's wrong, which is in all likelihood probably wrong, we will get it too low. Now it starts slowing down a little bit because we're doing all that calculations and stuff. So 433. Is that correct? I bet not. Yeah, it's too low. See, I was right. At least I had my mistake to... Okay, so what are we doing wrong here? Let's see if we can, when we get to the answer here, which locations we're missing. That might help. And what I just realized too is this might be problematic. No, it's... It might. It might. That might be a problem because in this case, if they're equal, Like if you came down from one and you're coming over this way, and so this hits here, and you realize, well, I might go that way or I might go that way. But you hit here and going this way is optimal. And for whatever reason, the cost of this one going this way ends up being the same as this one. We actually want that path included. Right? Because before we were just looking at the cost of it. We weren't looking at the actual path it took to get there. So I'm just curious. If I made that less than, and I took that test here, now it passes. They all pass. Let's see what happens now with this. So we do find a little bit more paths. You notice we're going up to like 600 now, but it doesn't get too out of hand. Ah, crap. It is. Come on. Somebody finish. Somebody finish. There we go. As long as it starts coming, it doesn't like spin out of control and we eventually start coming down. We'll just see what this does. Unfortunately, because we're keeping more paths around, that is making it struggle a little bit harder. I'm just hoping it can struggle to the point where it can get past all this. It went down there. It's going down a little bit. A little bit more down. It's going back up. Going back down. It's like a roller coaster. It's hovering. It's trying. And now it's going up again. I think once you hit, like, once you get one to finish, then the rest of them can start to fall off. You just got to get that first one to finish. And that was something I thought about as I was doing this. I'm like, do you just try to find, like, the shortest path, even though it might be not the smallest cost, and then do your evaluations based on that, because that might actually lend itself to, like, you just find the shortest path possible to get there, and that will give you a cost. And then you start evaluating everything that isn't that path. So now we're going up to 1600. It's trying. It's trying. Nope. Going down a little bit, going back up. Going down. Going down. Come on, baby. I'm wondering if we did actually hit and end. Going back up again. Going back up again. Going back down again. Going back down again. Going do boom. Well, okay. What did we have before that? Let's try this now. I don't care if that's not optimized. I don't care if that isn't the best way to do it, because I know it isn't. It obviously isn't. I'm going to put in, though, my notes here to say for day 16. Why are these over so much? Maybe get the shortest path using, I think, A star. Is that it? I can't remember. But there's an algorithm to say if you're given a maze and you're starting in a spot, this gets you the shortest path. And I just forget what the algorithm specifically does. Find its cost and then use that as a baseline as others find the true best path. Because arguably, and this isn't true, but I think it's a heuristic that the shortest path within a maze probably has a decent low cost. It's not always going to be the best one, because you might find a longer path that actually has a cheaper cost for whatever reason. But you just find the shortest path, and then as you're going through things, if you don't hit that, if you start going over that benchmark, you immediately wipe it out. So we don't wait until one finishes. That's something I may do as an optimization later on. But we finally can put 16 to bed. We can put it to rest for now. It is a gold star in our calendar. Okay, I'm going to skip over part 2 of 17 because, like I said, I don't have a good thought onto how do we actually do this. I have some ideas. I've been looking into it, some thoughts, but I don't have anything concrete just yet. So we're going to move on from 17. I am curious. If I look at the stats, obviously people have solved 17. Although you seem to have... And you get people to solve both. I mean, that's a given. So, whatever. 18. Ram run. Okay. Let's read it. You and the historian look a lot more Oh, wait. Before I do that, let's make sure. My older son is watching Happy Tree Friends, which is a hilarious but very brutal comic or animated video. Sorry, it took me a second. And so you got these, they're all happy, they're running around, all of a sudden just awful things happen to them. It's just hilarious. And he said, what I find so funny about Happy Tree Friends is that it genuinely feels like a kid's cartoon, just with blood. That was pretty funny. So, anyway, all right. So, by the way, if you've never seen Happy Tree Friends before, watch it. I find it funny, but it is very violent. But that's the point. It's these cute, cuddly little, they're happy tree friends. They're all very happy and yay, they're bouncing around stuff. And then just awful things happen to them. So anyway, moving back on to Advent of Code. You and the historians look a lot more pixelated than you remember. You're inside a computer at the North Pole. Just as you're about to check out your surroundings, a program runs up to you. This region of memory isn't safe. The user misunderstood what a push-down automation is, and their algorithm is pushing whole bytes down on top of us. Run! Eek. The algorithm is fast. It's going to cause a byte to fall into your memory space once every nanosecond. Fortunately, you're faster, and by quickly scanning the algorithm, you create a list of which bytes will fall. Your puzzle input in order they'll land in your memory space. God, one of these... This feels like what there was something in 2022 that like it felt very Tetris-y and things would fall down and you'd have to put them into space. And then like the first one, just doing it the way you're supposed to do it, part one, it was easy to do. And then part one's like, what happens if you had to do this 1 trillion times over? And of course you can't, because you just like part two of day 17, you can't. I found the upper and lower bounds of where the register A value has to be, but I don't know where it is in there, and it's like trillions of possibilities. So, but I know it's greater than 1. Okay, so we'll see. The thing I figured out in 2022, that problem is you have to find where it starts to repeat, and then you find that section of repeating, how long it is, compare it to like how much that is for 1 trillion, and wipe out all that, and then the remainder is what you still have to play out, and then you get the answer. So then it becomes really quick. Okay, so you create a list of which bytes will fall, your puzzle input, in the order they'll land in your memory space. Your memory space is a 2-dimensional grid with coordinates that range from 0 to 70, both horizontally and vertically. However, for the sake of example, suppose you're on a smaller grid with coordinates that range from 0 to 6, and the following list of incoming byte positions. Oh, okay, so the grid goes from 0 to 5, 0 to 5. They're saying that the memory space we're working with is 0 to 70. Okay. Each byte position is given as XY coordinates, where X is the distance from the left edge of your memory space, and so 5 would be the maximum to the X. Wait. Oh, 0 to 6. So it's a 7 by 7. Okay, got it. Each byte position is given as an XY coordinates, where X is the distance from the left edge of your memory space and Y is the distance from the top edge of your memory space. Right. You and the historians are currently in the top left corner of the memory space at 0 and need to reach the exit in the bottom right corner at 7070 because it's a 71 grid. But 66 in this example. You'll need to simulate the falling bytes to plan out where it will be safe to run. For now, simulate just first few bytes falling into your memory space. As bytes fall into your memory space, they make that coordinate corrupted. Corrupted memory coordinates cannot be entered by you or the historians, so you'll need to plan your route carefully. You also cannot leave the boundaries of the memory space. Your only hope is to reach the exit. This feels like what you just did on 16, sort of. Maybe. In the above example, if you were to draw the memory space after the first 12 bytes have fallen using dot for safe and that for corrupted, it would look like this. So we're up here. Actually, let me zoom in again. So we're here. You can take steps up, down, left, or right. But of course, you can't go off the map. After just 12 bytes of corrupted locations in your memory space, the shortest path from the top left corner to the exit would take 22 steps. Here marked with 0. So I guess I'm going to have to look up A star because I don't... now I have to... It has nothing to do with turning. It's just what's the best way to get to the end. Left corner to the exit would take 22 steps. Here marked with 0 is one such path. I don't know how else you could get to the end. Yeah. Simulate the first kilobyte falling onto your memory space. Afterwards, what is the minimum number of steps needed to reach the exit? Okay, let's take a look at the puzzle input. So this is, what is this, day 18? Is that what we're on? Day 18. All right, and I'm curious. We look at day 18. How many lines long is it? 3/4. So we're basically doing the first third of the file. Okay. So how are we going to do this? We basically just go through each one. We find out where all the corrupted spots are on the map, and those are essentially walls. We can't go through them. And then we need to do path A star. A search algorithms. A graph traversal and pathfinding algorithm has many fields to compare due to its completeness, optimality, and optimal efficiency. Given a weighted graph, a source node, and a goal node, the algorithm finds the shortest path with respect to the given weights from source to goal. Yeah. A path algorithm. So that's what it's doing. And like they said, as you start going through it, it starts getting worse because, it's got to find more. As you start getting near the end. And there you go. And so that path there, that was the quickest path. The following pseudocode describes this algorithm. I could just copy and paste this, right? Jeez. Whatever. Okay, well, the first thing we're going to do is get our parsing in play. Make sure we're at least finding what the map looks like, right? So let's make a solution day 18. And just to follow our conventions, we'll do that. Okay, and then we need the namespace to be 18. Okay. So we could put in like how far in the memory do you want to go? Like how many bytes do you want to process? So we say var, we're going to need a hash set of positions, right? And again, I know I've defined position numerous times in this, but var corruptions is equal to a new hash set of positions. And for now, we're just going to return an int because the path has to be no more than whatever, like, if you think of Pythagorean's theorem, what the worst it could be is 70 plus 70 is 140. So that's perfectly fine. I think that's the worst it could be. The best it could be is basically like whatever that, it's 70 squared plus 70 squared is equal to whatever that is, the square root, blah, blah. So you know what I'm getting at. Okay. So we can say return corruptions dot count. Great. And so we say for var I is equal to 0, I less than bytes to process, I plus plus. We get the position. Okay. Wait, that's got to be that. There we go. We can actually... we can say split on a comma. Because that's what it is, right? Yeah, it's just a comma. Okay. So we say corruptions.add a new position where X is position at 0 except int.parse position 0 culture info current culture. And then we say the same thing except for position 1. Come on. And we could do a little bit of an optimization here to say if for whatever reason like this, that doesn't. But is there any like... well, those are just because of those. But you have like a 1331. I think that's... I saw one of those. Huh. I thought I saw that more than... whatever. I would imagine that you're going to run into duplicates. And so you could even say like... if the line itself is not duplicated, then actually add a position. Meh. Whatever. So let's go into our solutions or our tests. And let's copy one of those. Let's see. 18. So you say day 18. And we can say part 1. And then we'll say solution day 18. Now in the actual test here, after 12 bytes have fallen, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that. Okay. So we give our input here, and then we say 12. And they're saying that the shortest would be 22. Obviously, this isn't true, but we want to see, are we getting the actual, like, parsing correct? So it fails, but we're basically seeing 12 corruptions. Okay. And so now, yeah, we're in debug mode. Let's see what happens when we run this test. What positions we get in corruptions. We have 12 here. Does that line up with what we see here? So you see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It also has 12. That's a good start. So now let's just, because these are unique, we can just go through them all. 5, 4. 1, 2, 3, 4, 5. That's 1. 4, 2. That's that one. 4, 5. 0, 1, 2, 4. 1, 2, 3, 4. That's that one. 3 is 3, 0. That's that one. 2, 1. That's that one. 6, 3. 0, 1. Oh, 6. 0, 0, 1, 2, 3. Yep, that one. I was just off by 1. 2, 4. 0, 1, 2, 0, 1, 2, 3. That's correct. 1, 5. That's correct. 0, 6. That's all correct. 3, 3. 0, 1, 2, 3. That's correct. 2, 6. Down there, that's correct. And then 5, 1. And that one. So it looks like we parsed this correctly. Okay. Which is good. Now we just need to say the A-star algorithm. And with that, I'm going to stop because I don't know how to do that off the top of my head. We now know in our space where all the corruptions are. And so if I come to my host here, we can at least get that set up. Okay. And we can say we're running day 18. I'm going to say 18, part 1. And again, this will be wrong. I know this. But we want to do 1024. Okay. And so let's come back up here now. And let's make it 18. What happens when we run this? We get the wrong file because we don't know what we're doing. 18 input. So we get 1024. Ah, that's interesting. So there weren't any duplications. You literally have in your 70 by 71 by 71 grid, all those are unique locations. Okay. Now we just need to find a path that is minimal. Okay. And arguably, if you're gaming the system, you could say, what is that direct line? That's the best it could be. And then the 71 by 71, that's the worst it could be. And it's going to be somewhere within that range, inclusive. Right? Because the worst could be where you have a diagonal going all the way across that blocks everything. And except the 2 endpoints. And so the only way is to go all the way around and come all the way down. And so that is possible that the worst could be the best. Highly unlikely, but that's the way it is. So what I'm going to do off camera is look up a little bit more on A-star rather than trying to come up with it myself. I know that's the, or at least look up generally what is the best way to find the shortest path between 2 points on a grid. That's what I'm looking for. And then I'll come back to that. Probably not today. I'm going to be doing some Splinter Cell streams this afternoon. At least 1, maybe 2. But for now, I think this is decent progress. I do not need hints. I do not need help. Even if finding the shortest path isn't the right thing I'm supposed to do or whatever, let me struggle. But I think I've made decent progress on 18. 16 is finally put to bed. We'll eventually come back to 17, but for now I'm done. So if you're new to the channel and you haven't subscribed yet, please do so. I would greatly appreciate it. I'm trying to hit that first goal of 1,000 subscribers, so Please subscribe to the channel, and I will probably be coming back with another Advent of Code stream Monday and Tuesday morning of this week. That's the plan. So, thank you all for watching. Take care.